Thank you for joining this brief presentation on the new Modulab XM DSSC system, a fully integrated turnkey system for measuring dye-sensitized solar cells and organic photovoltaics. In this brief presentation, we will cover the basic issues and problems to resolve with DSSCs and other organic-based materials. And from this, we will see what measurement tools we have incorporated into the Modulab system to solve these particular problems. Throughout the course of this presentation, we will focus on some key features and benefits, including the auto-run and auto-analyze data feature, and the optical design, with reference to the reference detection techniques for IMPS, list traceability and auto-calibration, optical design including 6 decades of optical intensity for a wide range of dynamic measurements. And finally, we shall explore some other additional applications for which this system can be used. So to cover the basic research highlights today for these DSSC systems, they are classed as third-generation electrochemical solar cells. And they are still in the research phase, as there is much work to be done in order to commercialize these systems. An interesting point, though, is that the number of citations in the literature has grown a staggering 2,400% since 2005. And this reflects the nature of the DSSC chemistry. In essence, they can be used as a complementary technology with other solar cell chemistries, such as silicon and thin film. And they can be used in applications and environments where silicon is not appropriate, such as indoor and diffuse light situations. So there's much interest in commercializing these systems. However, as is common to all solar cell technologies, we are seeking better efficiency, longer lifetime, especially with the new perovskite cells, the cell leakage of the electrolyte-based systems, and ultimately lower cost. So what do we need? In order to improve the efficiency, lifetime, and reduce cost, we ultimately need a better understanding of the chemistry of the cells and a better understanding of the physics of the cells. And this is at the heart of the concept of the Modulab XM DSSC system. And from the first day of this project, we have made use of world expert in this field, Professor Laurie Peter of the University of Bath in the UK. Professor Peter invented the IMPS techniques and charge extraction techniques which we heavily use in this product. He has over 30 years experience in semiconductor electrochemistry and has helped implement techniques used in this system. Indeed, the complexity of some of these tests is such that some tests, over 300 steps in sequence, are performed, and this is very easy to get wrong. So therefore, we are extremely grateful to Professor Peter to help us enable and implement these techniques correctly. So in essence, the Modulab XM DSSC has his expertise built in. So this is a cartoon kindly provided by Professor Peter from Bath University. And you can see this demonstration at the Bath EIS course held every year in the UK in July. We have an indium tin oxide layer here and an indium tin oxide layer here. And inside we have our electrochemical processes. We have our titanium dioxide or zinc oxide semiconductor, to which we have adsorbed a dye, hence the name dye-sensitized cell. This region here represents the electrolyte, and it contains a compound called the redox shuttle. The processes occurring in the cell are thus: a photon of energy comes in, and we generate this electron. And the electron diffuses via this particulate contact, via this particular substrate, to the back contact. If an electron can reach this back contact, we can do useful work. However, as the photon comes in and we generate an electron, what can happen, and indeed what often happens, is that the electron recombines with a species in solution, in this case the triiodide couple, and this is called a loss factor. So in order to better understand the physics of our cells, we need to understand the diffusion rate of the electron to the back contact and the electron lifetime, that is, the period of time in which the electron is free to move within the cell, versus the recombination rate. So this is precisely what we have implemented in the XM DSSC system. We need to characterize the electron diffusion rate, dN, electron lifetime. Improving the rate of electron diffusion and increasing the electron lifetime will give us better cell efficiency. We also need to measure the recombination kinetics, and this will improve the cell efficiency as well. Decreasing the recombination kinetics will improve cell efficiency. We wish to determine the quasi-Fermi level, and this aids us in analysis of the effective electron diffusion and effective electron lifetime to determine the diffusion length. And finally, we need to understand the fill factor, efficiency, and power max of the cell. In order to measure these properties, we have implemented the following techniques. Intensity modulated photocurrent spectroscopy for effective electron diffusion length, intensity modulated photovoltage spectroscopy and PV decay for effective electron lifetime. The recombination kinetics can be measured using impedance spectroscopy under varying light intensity. The determination of the quasi-Fermi level is facilitated by implementation of charge extraction techniques developed by Laurie Peter and the QFL5Y method, also developed by Professor Laurie Peter. And finally, we can measure the fill factor, efficiency, and power using IV curve measurements. All of these techniques are available as standard for the Modulab XM DSSC, and detailed discussions of these techniques will follow in future presentations. So the solution, Modulab XM DSSC, contains the following: an optical bench, dedicated DSSC software based upon the Modulab ECS platform, a potentiostat and frequency response analyzer for impedance spectroscopy and transfer function measurements, namely IMPS and IMBS. Each system is shipped with a Solaronics DSSC cell for comparison with customer cells. These cells are manufactured in Switzerland and are manufactured exclusively for Solartron Analytical. Furthermore, and something that we will cover in the next part of the presentation, the system is shipped automatically with auto and advanced measurement suites for ease of analysis. And finally, existing Modulab users can upgrade their system to become XM DSSC compatible. So now I'd like to spend the next few moments talking about the key features and benefits of the system, particularly the auto-run and analyze data, and then I shall move on to the optical design of the system. To highlight the first key feature of the system, we developed specifically a set of experiments and conditions such that new users to this field can use the complex techniques available. So we offer two modes of operation. One is called advanced mode, in which the system can be used by experts who can control the instrument in a multitude of ways, or alternatively, it is equally suitable to absolute beginners to this field. And I've got a short presentation to highlight how simple this system really is to use. So the first mouse click, we can insert an auto experiment. All DSSC-related experiments, including IMPS, EIS, IMPS, charge extraction, photovoltage decay, and so on, are automatically inserted into the experiment. There is no need for the end user to alter any of the pre-programmed parameters. Indeed, there are over 300 pre-programmed steps. Therefore, we do not encourage users to change the cell parameters or the control parameters unless they will operate in expert mode. A second mouse click, you simply run the experiment. This takes approximately 6 hours to run the entire experiment due to the stabilization between each experiment of the solar cell, and therefore we recommend running experiments overnight. And thirdly, we press the mouse to auto-analyze data. The next slide contains a real-time video of the auto-analysis of data. What I have done is I have generated some data using the Solaronics DSSC cell overnight, and will now analyze the data. So what we can see here is that we have a wide range of data generated, including the IV curve for the cell, the IMBS as a function of light intensity. These are different light intensities being shown. The IMPS as a function of light intensity. Once again, this is fully automated, therefore the user does not need to be present during these experiments. Impedance spectroscopy as a function of light intensity. Notice how the impedance spectrum changes markedly as we change the light intensity. And here are some examples of charge extraction as a function of drive voltage. So that's the data file that's created automatically. Once you've got the data file, you simply press Export to Excel, and Excel will automatically open. And the data set has been analyzed. This is the full data set for the IMPS, where we've characterized the diffusion coefficient as a function of voltage. This is the IMPS, electron lifetime. This is charge extraction, charge extraction dark, and analysis of PV decay. Fully automated. That was a real-time experiment. So here's some examples from the auto analysis, including diffusion coefficient as a function of photovoltage, and notice how the diffusion coefficient decreases as we decrease the voltage. The electron lifetime as a function of voltage, and again this is the electron lifetime as a function of voltage using the PV decay technique. And these are invaluable tools because they help the end user understand how the chemistry and physics of the cell are affecting the things like the diffusion coefficient and the electron lifetime. As I said at the beginning of the presentation, what we want to do is optimize diffusion coefficient. In other words, make it as fast as possible. We want the electron lifetime to be as long as possible for better cell efficiency. So one could, in theory, overlay many plots of diffusion coefficient for different cell chemistries and electron lifetime for different cell chemistries and compare and get a much better understanding of how the chemistry is affecting the efficiency of the cell. So clearly the benefits of auto-run and auto-analysis are as follows. Ease of use. Even beginners to this field can analyze complex techniques such as IMPS and IMPS and run and analyze data with no previous experience. These are all pre-programmed tests, over 300 steps in a sequence of experiments. And this is non-trivial, and we could only achieve this through the help and dedication of Professor Roy Peter. Productivity. Whilst you're running these tests, you can do something else. You do not have to be at the optical bench or the system tool in order to change anything of the cell, such as the light intensity or cell or current control of the solar cell. And finally, you can generate your results fast. You can understand your cell chemistry faster than other groups. So the second part of my presentation, I want to focus on some of the features of the optical bench design. Clearly this is an optical measurement system, and therefore due care and attention must be given towards the optics and correct implementation of the optics. And so the features I'll be discussing include NIST traceable measurements, a sample reference technique for IMVS and IMPS, an auto-calibration routine, and finally 6 decades of light intensity. Well, that's a change in the order of 1 million times change in light intensity available with this bench, offering us a wide range of measurement properties. I'll firstly start with the reference detection technique for IMPS and IMVS, and this was developed by Professor Peter once again. And it was developed to eliminate errors in phase and magnitude by using a reference signal which is the same phase and magnitude as the light on the solar cell. And this is from a paper from 1989. This is from ChemRev, and Professor Peter used a Solartron 1286 and 1250 for these results. So in essence, we take the generator signal from the frequency response analyzer, the sinusoidal AC signal, and we input this into what we call a light acoustic modulator. And this will produce a sinusoidal light waveform, which we will then excite to our solar cell. In this case, he's using a 3-electrode cell. What Professor Peter developed was the reference signal, and so 50% of the light actually is diverted into a photodiode, and 50% of the light is diverted to the device under test. And therefore, we compare the measured light, the measured phase and magnitude of light at the photodiode with the response from the cell. Because at high frequency, what will actually happen here is that the modulator will attenuate and introduce phase shift of the frequency response analyzer generator signal. And this will then introduce errors in phase and magnitude when we measure the IMPS and IMPS response of the cell. So if we measure this reference signal, it's in precisely the same phase and magnitude as the input to the device under test. And therefore this eliminates phase and magnitude errors. Errors in phase and magnitude will distort the effective diffusion coefficient and effective electron lifetime results from IMPS and IMPS. So this is a critical part of the system. However, we've taken this a little further. So working with Professor Peter, we've taken the bench to the next level. We now use high brightness, thermally stable LEDs. High brightness LEDs give us the ability to measure the performance of the cell over a wide range of light intensities. But in addition, our LEDs have been specially formulated and created to be thermally stable. What can happen, and indeed what often happens with LED-based systems, is that the output of the LED changes during the experiment, and particularly for experiments such as impedance spectroscopy and IMPS transfer function techniques, It is critical that the input, i.e. the light, is stable during the course of the experiment. If the LED has not been optimized to be thermally stable, then the output will change, thus invalidating measurements. In addition, LEDs have a long lifetime, greater than 50,000 hours, and can easily be modulated. So they are the perfect tool, and indeed Professor Peter now uses the same LEDs that we offer with our system. In addition, we have condensed sample reference detection technique and make use of NIST traceable calibrated sensors. And this is the optical arrangement for the sample reference detection technique. And so a beam of light comes through into this cube device here. This is called a beam splitter. And 50% of the light goes onto the reference detector, and 50% of the light carries onto the solar cell, the device under test. The critical thing here is that the distance between the reference detector and the distance between the solar cell from the beam splitter are identical. Therefore, the intensity measured by the photodetector and the intensity measured by the cell are exactly the same. And that's how we generate a good reference signal. This is described as a fixed position optics system, and I should explain that in further detail in a moment. But in essence, there is no need ever to change the position of the reference photodetector with respect to the solar cell. Therefore, the chances of introducing unwanted errors are very low. In addition, we've included neutral density filters. A neutral density filter will attenuate the intensity of the light source. And in our case, we supply a neutral density filter that attenuates the signal by 1,000 times. So this gives us the ability to change the light intensity over 6 orders of magnitude and allows us to probe the performance of the cell over an enormous range of dynamic conditions. And finally, we've produced a highly focused and homogeneous beam of light for high brightness studies. And this is very much LED dependent, but for even our low power LEDs, we generate greater than 0.1 sun equivalent power on our solar cell. And in this case, we've got a red homogeneous beam. So as an example of how low light studies can help extend the range of measurements, this is some data from a typical type of measurement using the neutral density filter. So this is the optical arrangement. The size of the optical bench is exactly the same size as an Apple iPad, so therefore gives an indication of the compactness of the optical design. And incorporated in the design, we have this neutral density filter, which is in the path of the light beam. Therefore, we can calibrate the effect of the neutral density filter has upon the light intensity. So this experiment here is the photovoltage, and we've just measured some trapped charge in the solar cell. And what we show here, that in this lightly shaded region, this is the effect of adding the neutral density filter. Everything above this line we can measure without the neutral density filter. However, we cannot drive the LED to low enough light levels without the neutral density filter to access this range of information. So with the addition of the neutral density filter, it's extending the range of measurement possibilities. And for those of you new to the solar cell field, this extension of range here of 250 millivolts, 200 to 250 millivolts represents quite a large change in the performance of the cell. So there's a lot of interesting and important features to understand in these low level conditions. And part of the reason that we can also go down to low light intensities is that we make use of an amplified photodetection stage. And this has been specially developed for Solartron Analytical, and I should explain that in a moment. A third benefit of our optical system is that all of our measurements are NIST traceable all of the time, and there are no exceptions. The criticality of NIST traceability is to ensure reliability, repeatability, and confidence with results. What is often happening in this field is that samples are being prepared, for example, in Japan, and then being tested perhaps in the United States or in Europe. And it is critical that the continuity and repeatability of tests between Japan and where they may finally be used is consistent. Therefore, we offer a NIST traceable measurement system. Therefore, we can eliminate errors associated with poor optical design. All of our measurements are quoted with respect to milliwatts per square centimeter, and the system is shipped with this NIST traceable amplified photodetector as standard. And as I mentioned earlier, this is a fixed position optical system which guarantees reproducibility. And this is critical when comparing data sets from one research group to another. You can see on the amplified stage here we have different gain stages. And so this allows us to measure very low-level signals and amplify those signals such that we can resolve them easily and measure them on our measurement system. Finally, the NIST traceable calibration is complete in less than 2 minutes. And I've got a video to demonstrate this. This is a real-time calibration. This is the calibration screen in the software. And I'll just start the video. So we press Calibrate LED. And the software automatically warns the customer that the system is about to perform a calibration. And it tells this customer how to connect the cables for the calibration. It is a very straightforward process. It also reminds them which gain setting to set on the photo amplifier, and off we go. There are two methods of calibration. We have to calibrate for software control and calibrate for hardware control. But as far as the customer is concerned, this doesn't matter. This is all fully automated. So now we're performing the calibration, and it's going to store a calibration file. So once we've finished that experiment, which is about 2 minutes in duration, this is a typical calibration file. So the curved line represents the software control, and the step line represents the hardware control. So we have two methods of calibration. But now we have this calibration curve, we know what the output is in terms of milliwatts per square centimeter as a function of drive power of the LED. So all data points now are referenced to this calibration file. You cannot run an experiment without a calibration file. So every single measurement has a calibration file associated with those measurements. So there can never be any arguments about changes in light intensity. In addition, one can compare calibration files over time to determine the LED degradation. And all calibration files, once again, are NIST traceable. Finally, we have a wide range of LED options that can be purchased from 400 nanometers to 700 nanometers, and this list is not exclusive. We do have the option to extend the range of the bench into the UV region, and if you have measurements and measurement needs to move into the UV region below 400 nanometers, then please contact an Ametek representative. Finally, some brief indications of where these techniques are being used in other applications. One of the most exciting fields at the moment is water splitting. And this is the generation of hydrogen and oxygen, primarily hydrogen, for fuel cell research. The use of IMPS and IMVS in this field is becoming a common technique. And Professor Peter has done much work on this, so I urge you to look at the literature if you're interested in this field. We can also use a system for photoelectrochemical measurements. One of the things that has been incorporated into the system is the ability to run classical standard electrochemical techniques such as cyclic voltammetry, chronalphometry, potentiostatic impedance, galvanostatic impedance under light control. So you can develop and build your own photoelectrochemical measurements. And finally, it can also be used for organic solar cells, which I haven't covered in today's presentation, but will follow soon. So thanks for listening to this brief presentation, and please keep watching. Coming soon, we have new presentations including the analysis of the IS data and how to model DSSC data using ZView, hardware considerations for these transfer function techniques, and technical notes on charge extraction techniques.